Okay, hello Bitcoin class. So I'll call this one somewhat optional. This is more for the computer science, mathematics sort of side of people. I don't know that you need that much to know about how this works, but let me add a few bits of what happens in the core of this whole public key cryptography kind of idea. So I guess I want to talk about finite fields to start with. So what is a finite field? So in algebra classes, that sort of stuff, you have spent time learning about the rationals and reals and that sort of stuff. And so the not finite fields is really rationals like 7 over 18, right? And -1 and 0, those kinds of numbers. And also the irrational numbers like square root of pi and e and those sorts of numbers. You have worked with, I believe, in the past, and there's basic arithmetic, right? You can add them, you can multiply them, you can divide them, as long as y is not equal to 0. And then there's nice rules that allow you to simplify expressions, right? So let's see here. So in particular, I think the thing we'll eventually get to on this side is a pretty simple idea that, how does this work? So if you take some number and raise it to a power, right, and then raise that to another power of that you end up with the same number as you took x raised to the n times m, like that. So x to the cubed to the 7th, like that. I guess pick any number you want in there. X to the cubed to the 7th is the same as x to the power 21. And that's the same as writing down x to the 7th and then cubing the result. So taking x, multiplying by itself 3 times, and then taking that number and multiplying by itself 7 times is the same as taking x and multiplying by itself 21 times, which is the same as taking x and multiplying it by itself 7 times, taking that result and multiplying it by itself 3 times. So of the various properties in the algebra systems, here's one that seems to be particularly handy, or like kind of where we're heading to. All right. But finite field, there's a couple of them, but instead of these quite like infinitely large sets of numbers, it turns out that you can have a finite number of elements and really enjoy essentially all the properties that you're used to from algebra about the things that are in that set. And so if you pick a prime, prime number is a number that is indivisible by anything but itself, and 1. So 2 is considered the first prime, and 3. 4 is not prime because 2 goes into it, but 5 is a prime. And then the list actually goes on to infinity. There's always a larger prime. But pick one, let's say 5. Then think of the numbers of 0 out to p minus 1. So in our case, it'd be 0 out to 4, like that. So if you do arithmetic, what's called mod p, arithmetic, then what that means is you take like this normal sort of addition, for example, you do x plus y, but then the result you consider remainder p. So like what's the leftover after you divide by whatever prime you decided to stick on the end of this thing. So for example, if I wanted to, in this case, if I did 3 plus 2, if I was working in this mod p world, well, the intermediate result, thinking about it over here, would be equal to 5, right? But then mod p, mod 5. So when you divide by 5, what's the remainder? That's actually 0. So in the mod p world where p is equal to 5, we have this odd thing that 3 plus 2 is just equal to 0, like that. So it turns out that the rules of arithmetic like this actually all work out. So in what odd way? So maybe surprisingly, right? So over here in the regular numbers, 3 plus -3 equals 0, right? Well, 3 plus, it turns out 2 is the opposite of 3 in the sense that when you add it to 3, you get 0 in this mod p arithmetic. So in this arithmetic, -3 is actually 2. So the opposite of 3 is 2, because when you add 2 to 3 in this mod p arithmetic, you get 0. So there's a similar sense of division, which is interesting. So I don't know if I want to spend too much time. Let's see, 3 times 2. Well, let's see if we can find what times 3 will end up giving 1. So it's not 1. 3 times 2 is 6. Ah, there we go. 3 times 2 is 6, right? But 6 mod 5, well, that's 1, right? So 5 goes in there once, and there's 1 left over. So 3 times 2 in this mod p arithmetic gives you 1, all right? So it turns out that, right, so over here it'd be 3 times 1/3 is what gives you 1, right? So what's true in the mod p arithmetic is 3 inverse, or 1 over 3, if you like, is actually the number 2 in this case, because the number 2 times 3 mod 5 gives you the identity, the number 1 over here. So, okay, so in this mod p world, for every x, there's another number x which you can think of as minus x, like this sense. And then down here, for every x that's not equal to 0, you can find a number that you can think of as 1 over x, like that. And this is only true if x is not equal to 0, like that. So in this finite field, you have these properties, and then I guess in this, hopefully it doesn't surprise you, you also get these other properties like x plus y is the same as y plus x, and x times y is the same as y times x. So all the properties, essentially all the properties of what you think of as a regular field, the ones that you maybe worked with before, actually work in these finite fields. And so you get some nice properties out of it, all right? Okay, so in finite field arithmetic, let's talk about the next thing. So finite fields, it turns out that the p that's interesting is a very large prime. So instead of being a number like 5 or 6, p is very close to 2 to the 256 minus like a tiny number by comparison in this thing. So the prime that is involved in the finite fields is just really large, all right? So the finite field arithmetic is works with these large points, data points. Okay. So the next step is this thing is called an elliptic curve. And I believe the formula in the one that's used for Bitcoin is actually this particularly simple looking formula, all right? But this particular formula is done all mod p, where p is this large, very large prime number, right? So the points in here are all numbers between essentially, well, they're slightly smaller than 2 to the 256, right? And if you think about the values of x and y that make this true, it turns out it's a curve that kind of goes out this way. And okay, so then there's a sense, this is layers upon layers. So we already have an idea of multiply here, and we're going to find a second kind of multiply. So if you have an x and a y, let me draw a different direction. If you have a point here and say a point here, you can draw a line through this curve and you get a point here. So if this is x and this is y, then you might consider this, it's just an action, right? So you have 2 points on the curve, and then you take, oh, sorry, be more careful. So a point on the curve satisfies this. So we'll call this x1, y1, and then this is x2, y2. So this point lies on the curve, this point lies on the curve, all right? And since they lie on the curve, then as an elliptic curve, you would expect that there's a point of intersection somewhere out here. And so we call this A, we call this point B, which is actually a pair of points in the field, all right? Then you could get a point C, which you could call A times B. So if you have these 2 points, and then you look at the point that curve intersects with, then you get another point, which would be you could define as the product of those 2 points. And so maybe a thing to notice then is if you flip the sense of B and A, then the intersection doesn't change. So you have this idea that x times y is the same as y times x if you use that rule, all right? But it gives you an idea for what multiply could mean, all right? So in this setup, what you do is use a point. You have to use tangent lines. So what you mean by, sorry, I've got one little detail, I think. So what if A and B are equal to each other? What do you do there? You use a tangent line and look at the intersection point that way. So you can also define what essentially is A plus A. You look at how that intersects. That, I guess in this case we get to infinity on that one. But in many cases, when you do the intersection point, you get a different point on the curve. So you can define what A plus A means by thinking about tangent lines. And then you get a completely consistent version of what do you mean by this operation, this times operation. Okay, so if you have a times operation, then you can repeatedly use it, right? So you can define x cubed as x times that star x. Oh, let's not use x then, because that is x and y. So you can think of a cubed as a times a times a that way, right? So a raised to a power is really doing this multiply step multiple times like that. And so then you get this rule, right? So with this idea, and since it commutes, you actually, for any point on here, you do have the property that a raised to some integer power and then raising that to another integer power is going to give you the same result as a when you swap them around, m raised to the n power. So take a point on the curve, do this tangential action n times, take that point and do it m times. You'll get the same result as if you did it in the opposite direction. All right, so if you stick to if this is some secret, right, a to the n to the m, oh, sorry, that's just a generator point. So this could be the generator point, all right? And then one of these could be like a secret. All right, so over here is the secret too. So what's interesting is if you have g raised to the n, right? So if you have this value itself in secret, and you raise g raised to the n, then anybody else can raise that number to the nth power, or that point using this to the nth power, and that's actually pretty easy. But having g to the n does not easily give you n. You can't, it is hard, how do I say this? This sense of multiply, let me put it this way. So this sense of multiply, where multiply means g to the n to the m like this. So this is easy. But if you knew this result and you just wanted to find like the inverse of this, which in algebra notation would be n to the m. And then say if you wanted to undo the mth power, then you'd raise it to the 1 over m. Sorry, to the 1 over. This, undoing this is hard. So with this set of arithmetic steps, it's easy to take powers and raise it to other powers, but if you have the power already, you can't undo this step easily at all. It's actually a very hard step. And so basically, so that's a lot of chain, and I'm not saying, and again, so students that are not interested in this stuff, you don't have to worry about it. I just thought it'd be interesting to kind of introduce how it works. But the core thing is that there's an operation that they call multiply, where multiply is easy, but divide is hard. All right, and so the basic mechanism. This is like the one-way door. So if someone takes a secret key and multiplies it by a generator, then that can give you a public key. And the thing is, the public key, you have to divide by the secret key in order or I guess you have to divide by the generator in this sense to restore the secret. It's not easy to do. But if you have the secret, it's easy to make. And so there's the core sort of step that happens in this elliptic curve encryption. So, and I know there's a lot of stages in there, but I did want to just introduce the core idea of it for people with a more mathematical inclination, kind of understand like what is going on here. So these secret keys are points on the curve, and those points are then worked through that diagram as a multiplication many, many times, and there are algorithmic simplifications for that. No details there. And then that derives a public key, which is another point on that curve, right? Because each multiply creates a new point. Something, maybe there's one little bit of information that's kind of nice to share. Like a point on the curve is really an x coordinate and a y coordinate, right? There's an x, y coordinate for a point on this curve. So these are numbers between 0 and p minus 1, right? Where p is a very large number. To reduce the amount of information that's necessary to write down about the keys, what's true? The y coordinate is actually not very, very interesting, right? Because the y is either the plus thing or the minus thing. Kind of the x looks pretty interesting, but the y is, are you up or are you down? And that's back to the y squared equals x cubed plus 7. So basically, if you know the y value, the only thing it's really missing is are you above or below, right? And so, so really the y value itself is not that interesting. And so basically, what is interesting is are you on the top or on the bottom? So basically, you need information for the x and basically the sign for whether you're on the top or the bottom of the curve, and then that reduces the amount of information that's kept in the block. So these segregated witness keys just compress the amount of information down so that you don't need twice. X and y by themselves are two relatively large numbers, right? But if instead you just write down x and then which curve you're on, then you get a more compact version, and that matters a lot because of the transaction limits. If you can shorten the points that you're talking about, then the key sizes, the lengths of the transactions in terms of bytes written goes down substantially, and so that essentially allows miners to put more transactions per block into the transaction. And so that's a simplification that happens in the protocol. So we are not going to ask you any particular question about elliptic curve encryption or finite fields. I just feel like it is an interesting part of what is modern computer security that uses finite fields a lot and elliptic curves. Your day-to-day existence as a person who feels like your data is secure has everything to do with the mathematics behind these things and the computational simplifications that happen. But for the people that are mathematically or interested in math or computer science or computer security, I hope you find this stuff at least somewhat interesting because it is at the core of a vast number of transactions and protocols. All right, thanks very much.